times 4 choose. Sorry, I meant for the next one. This one's whatever. We'll get it filmed and we'll explain it. Get the whole board. We'll recap the question again. And we'll... Good? Okay, so the question was, you're drawing 4 cereal boxes from a sea of cereal boxes. Let's say every box has stuff inside it, whatever. There are 7 different types of things that can be in the box. We assume an infinite amount of each box type. So therefore the question is not hypergeometric, it's binomial, because for hypergeometric, probability of success and failure change as time goes on with trials, because you're removing successes or failures from the pot, which drops the total amount of the pot as well as the number of successes or failures, which means P and Q would change. In this case, if we assume an infinite quantity of everything, it doesn't matter if you grab something out of the ocean, you grab a drop out of the ocean is still the ocean. So we assume P and Q is roughly constant. Therefore, the problem is binomial. So, but I said, let's hold off on using a binomial model first. We just used some logic. We said, okay, go linearly first box. You're always going to be successful whether you choose box 1 type 1, 2, 3, 4, 5, 6, or 7. But then once you've chosen one of those types and you've chosen box type 2, you've got to grab 2s the rest of the way, and there's only 1 out of 7 for 2s the rest of the way. We talked about order being counted for the denominator and for the numerator. Although you only have order stage counting for these 3 stages, it doesn't matter, because if you think about it, there are only going to be 7 possible orders. 1 order per type. In other words, all box types 1 or all box type 2s, 3s, 4s, 5s, 6s, or 7, 1 for each. That gave us 7 over 7 to the 4, which is 1 over 7 cubed. Then for the hell of it, we tried modeling this thing using a binomial probability distribution. Yep.
Aren't they
let me finish. Using a binomial distribution, where it's just px is equal to entries xp to the x cubed n minus x. But if you wanted to use binomial, you had to set up 7 distributions, whereby the random variable x had to be split up into an x1, x2, x3, x4, x5, x6, x7. x1 we defined as the number of box 1s you get out of 4 trials. x2 the number of box 2s you get out of 4 trials, ... x7 the number of box 7s you get out of 7 trials. And therefore we had to calculate the probability of getting 4 out of 4 for each of the types 1 through 7 for each distribution. For box type 1, that means 4 out of 4. Probability of success is 1 over 7 to the 4. Failure is 6 over 7 to the 0. You end up having the exact same arithmetic for all 7 distributions. So when you add these together, it's the same as just multiplying 7 by any one of these 7 results. This goes to 1, this goes to 1. You end up with 7 times 1 over 7 to the 4. You get the same solution. Then Milad said, so I said, you know, you don't have to use this crap. It's pretty sophisticated. We could have just used this simple logic. But then Milad is saying, well, for the other questions, maybe it'll just be easy to use this thing again and again and again. So for part 2, probability of getting 3 identical is going to end up being 7 times 4 choose how many?
3.
Right? Times probability of getting, we have to remember, you're doing 7 different distributions, which are all giving you the same result, right? So for any one of the distributions, the probability of getting that 1 is still 1 over 7, right? But now you're raising that to the 3, you've got the 6 over 7 to the 1. Remember, these have to sum. Okay, what's question number 3?
2 identical and 2 different cards.
That's different. Because, can I just use the binomial for this? No. Because does binomial ensure that if you get 2 identical, that the other 2...
They might be identical too.
Exactly. So you're going to overcount, right? You're going to overcount. Go ahead. What, Milan?
My question was, over there, aren't they physically different?
What is
For
there?
the order, you were talking about the order. Aren't those 4 boxes physically different?
Yes.
So then there must be order.
Yeah, but when you flip a coin, right? What's the probability of getting, if you flip 2 coins, probability of getting both heads is what? 1 out of 4, right? Probability of getting head and tail is 2 out of 4. I agree. When the results are different, and you can get the same result by flipping the result of each of the boxes, because it's physically a different possible outcome, fine. But when everything is identical, there's only one way it can happen. In this case, everything is identical.
So I think that is y as well. Up there is y.
No, this isn't a y. Why is this an x? Because 7 corresponds to the total, x is the total number of box types. And in the numerator, right? How many box types are possible at the beginning of your tree? Any one of the 7. Right, look, here's your tree. Look, once you pick box type 1, what are you forced to pick? What box type are you forced to pick for the rest? 1s. If you pick box type 2, what are you forced to pick for the rest? 2s. How many orders can there be if you got all box type 1s? 1. Right? If it's like, what's the probability of flipping a coin 7 times and getting all heads? How many orders are there? 1.
But why is that X? Why isn't it Y?
Well, because I'm defining this as X.
Okay, but that top 7 is different.
No, it's not.
It's 7 possibilities. The bottom.
What are these 7? What is 7 defined as here?
7. You have 7 boxes.
And what is this 7?
You have 7 possibilities of.
It's the 7 kind of boxes. It's the exact same thing. This 7 is the same.
The first stage you have 7 choices and then you can choose from 7 boxes.
Yeah. The reason why this is a Y is a subset of X. Because once you've chosen one of those 7, you have to choose. Once I've made that choice, I can only take 1s. Right? So, anyway, where is it? Okay.
So why would you overcome the binomial on this third one?
Because in the third one, because this is a probability that you have 3 identical. Maybe you have 3 4s and a 2. Okay, Archer, get in here. Janice, 2d10. Maybe here you have 3 3s and you get a 1. Okay, but here, if you do the binomial's number of successes, now it's asking you for getting 2 the same and 2 different or something?
Yes.
But binomial doesn't talk about the way in which you fail.
No, but
binomial just cares that you get the 2 identical 3s.
No,
but maybe you could get double 4.
If you put x equals 2, you get 2 failures, for sure.
Yeah, but a failure could involve 2 of the same, of the wrong type. If x1 is defined as the number of box 1s you get out of 4 tries, right? And you say, what is the probability that x1 equals 2? That means you have a pair of 1s. That's it. What happens with the other 2? Who cares as long as they're not 1s? You could get a box 2 and a box 4, but you could get a double 4, which is violating the rules that you just said. So I can't use them. Does that make sense? How many of you guys understand that? Oh, yo, my. Gone completely?
That part, yeah.
Okay. Look at this formula. We developed this formula. We proved it. It's a binomial formula. It says that the probability. What is x? What is n? What is n? Number of trials. You roll a die 10 times. What's the probability? And you define success as getting the number 5. X is the number of times you get a 5 out of the 10 rolls. You could do it 10 times and never get a 5. You could be super lucky and all 10 rolls could be 5s or anything in between. X can run from 0 successes up to 10 successes. Let's say X is equal to 1 success. You rolled 1 5. That means the other 9 rolls can't be 5s. Could they potentially be all 6s? So you could get 1 5 and all the other rolls be 6s, right? In any order. That's what the n choose x is for. It jumbles up the order. Now, in this question it says, what's the probability that you get exactly 2 of the same? So here we're talking about 4 rolls in this question, or 4 boxes. What's the probability you get exactly 2 of the 4 are the same? Maybe 2 box 1s, or 2 box 2s, or 2 box 3s, or 2 box 4s, right? But let's say you get 2, let's say you get 2 box 2s. The other 2 boxes, the only thing the binomial distribution knows is that the 2 of the boxes are going to be box 2s, but it doesn't say anything about the other 2 boxes. Couldn't the other 2 boxes come up as double 4? But in part 3, you guys are saying the question is, what is the probability exactly 2 identical? Right? Meaning it doesn't want to allow for double 2 and double 4. It wants like double 2 and a 3 4. Binomial distribution counts both.
Sure, but in the question...
So if you want, you could use binomial If you want, you could use binomial, but then you have to subtract all cases where you get two sets of pairs. Right? You want to do it that way, or do you understand what I mean? Which way do you want to do it? That would be indirect. You want to go direct or you want to go indirect? If we use binomial, we got to go indirect. We got to subtract cases. If we go direct, we just use the logic like we did up there. What do you want to do, Krish?
Direct, why not?
Okay, let's try direct. Let's think about it. Okay. I don't know, there's so many ways you can do this. There are 4 box types, right? I just use whatever comes to mind. I'm going to choose one of them, and I'm going to call this choice, I don't know, T. And that's going to represent choosing, it's like when we do cards, choosing a box type for doubles. You know what I'm saying? In other words, I'm going to take a pair of box 1s or a pair of box 2s or a pair of box 3s. There are 4 possibilities. You can either have double 1, double 2, double 3, double 4, right? Now, once I make that choice, I need to grab 2 singles, right? From how many choices? 3, right? I can't go back. And I got to take 2 singles. This is TU. This is 2 singles, right? Now, is there any order in that yet? There's no order in there, right?
No.
So let's put it. Where's the order?
There are different objects.
Thank you, T and U. Somebody's learning finally. Somebody's understanding this stuff that I write on top of the things. You think I write this crap for no reason?
Yeah.
No! The book doesn't give you that. I try to give you a little bit more so that when you get to complex questions, not like this one. So you have to inject order now. So how many objects are there?
2.
What?
4.
So 4 factorial?
Divided by?
3 factorial.
The same thing, the same.
How many of the objects are identical?
2 factorial times 2 factorial.
My bloody birthday here. Come on, work with me.
So we can say yes all the time, yes.
And what do you put on the denominator? At least tell me you know how to do that.
4. 7.
Put those 2 numbers together.
28.
Why would the denominator change?
74.
Wouldn't it be the same thing?
70.
So not 74.
Looks like 70.
7 to the power of 4.
Because you have 4.
It's the same as this one.
So are you crying?
No. I don't know what happened. I've taught you guys all semester. Okay, now, you want to try it the indirect way?
Yeah. That's it?
Who solved it a different way?
Wait, that's it?
That's it. That's it.
Yes!
But like...
Oh shoot! Thank you. Very good. Well done. Nice.
Also, there's something else.
What?
Okay, so when...
Why did I multiply by 7? No, wait a minute. Wait, you're confusing me. I don't think I need this.
Yeah.
I never said you need that. I was talking about
This is
something
good.
else.
This is good. Because I have it for any of the types. Yeah.
So when you choose one of the types to take a pair, shouldn't you take that pair 2 out of 4? Choose 4, choose 2. Is there a physical difference?
So remember, you're picking cards from the boxes.
Oh, are we assuming that these things are identical?
No, what happens is that you get 4 boxes, and you're picking cards from there. The boxes are all the same.
There's 7 types of cards.
Yeah, but there's 7 card types.
Yeah.
No, it's just
Wait. Oh, it's 7 card types, not 4.
Yeah.
Okay. So this is a 7. This is a 6.
Oh.
Yeah, sorry, I forgot. I was mixing everything. Yeah, there are 7 types,
You
right?
have to change that too.
Yeah, that's 7, that's 6.
So don't you have to change that then?
Change what?
7
those
factorial.
things.
No.
This is for the boxes, right?
But yeah.
Yeah, because this is the box types. There were 7 box types. It's like if you had 2, 3, 4, if you had 2, 3, 4, 5, like in cards, right? You had the options 2, 3, 4, 5, 6, 7, and 8. You had 7 different options. You got to choose one of those cards to be a pair. And then once you've chosen that to be a pair, you have 6 cards left, and you have to choose any 2 of them to exist once. Now, unlike in cards, we're not putting suits on the box types. So we don't have to worry about that. But we do have to do multiply and jumble the order of possibility of choice. Because, why do we have to create order here? Because we're creating order here. If you actually ran the experiment and grabbed all 4 boxes at once, right? Here's a good question. Here's a good question for you. If you ran the experiment and you just grabbed all 4 boxes at once, should the probability be different? Remember, we proved this. No.
Oh yeah, because you divide the same thing.
But here's the whole course again. But the problem. But how would I solve this question with? So I did. But the problem is, okay. So you're agreeing with me that if you take them one at a time or if you take them all at once, it makes no difference on the probability. But what's the easier calculation here? The denominator. And does the denominator count order? So therefore, guess what? You've got to count order for the numerator. Because you've gone with the order counting method for the denominator. Why is it difficult to remove order from the denominator there? It is. This is called same variable without, how did I write, what's my thing for it? Same variable, this with replacement. This with replacement thing will kill you. Why? Because that 7 to the 4 has cases where you have all identical the same, all identical, which means one order, but it has cases where all 4 are different, which means 4 factorial orders, and cases where 2 are identical and 2 different. Remember, like with the twins at the beginning of the year, you have to break it up. So to remove order from this, can you just take this and divide it by 4 factorial?
No.
You can't.
You can't. You idiot.
If you took this, okay, watch. So if I just didn't put the order in here, right? If I did this without order, it's wrong for some reason, but if I take that denominator and divide it by 4 factorial, am I undercounting the denominator or overcounting it? Here's a question for you. If I take this denominator and say I want to remove order, and I just divide by 4 factorial, have I taken away too much order or not enough?
No, you're taking enough.
Not enough.
Too much!
Why?
Because some of these 7 factorial cases are cases where you all have box 1. And you're going to be dividing that by 4 factorial, but how many orders are there for all identicals? 1. The only cases within that 7 to the 4 that should be divided by 4 factorial are all different. Like, whatever. Case A, B, C, D. Right? That can be jumbled up 4 factorial ways. But they're mixed in with cases of double A, C, D, or maybe 3 A's and an E, right? Can't separate that. And it's because it's with replacement. It's same variable, but with replacement. Same variable, no replacement, easy. You can just divide by 4 factorial. Why? Because if you choose your first one as 7, let's say box type 7, and then you're down to only 6 types, 5, then 4. When you look at your tree, you'll never ever have the same box type again. You'll have, any branch you follow will have 4 different things. So you just divide by 4 factorial. Same variable with replacement, that'll kill you. If you go and try and treat it, do one treatment for order removal or rejection, done. So we went with order here, so therefore we must go with order here.
You can minus the thing, like you get seven kinds, just 7 kinds which are identical. So you minus it and then you divide it by the factorial. Can you do that? Like you minus all the possibilities for the identical things.
Yeah, but you have to what you have to do is you have to break it into all cases. All same, 3 same, 2 same, 2 different, 2 same, 2 same, all different, whatever. And then you'd have to remove the according order from each of those cases, add it all back together, would give you a new denominator, right? And then you would take this away. You know what I mean? That's disgusting, right? Since we've already proven that you would get the same answer, why would you do that? We proved that with the, right? But if you wanted to, you could break the 7 to the 4 up into all the cases. For identical cases, how many cases would you have where all are the same? 7.
7.
So you'd have 7 cases where you'd leave those alone. You wouldn't divide by anything. Then you'd have 7 cases of, let's say, 2 same, 2 same. And how would you take order out of those? you would divide by
2 factorial multiplied by
4 factorial over 2 factorial, 2 factorial, right? And then you'd have a bunch of 7 times you'd have A, B, C, and you'd go like this. And then you'd have some cases like this, where you divide by that. And then you'd have some cases like this, where you would divide by that. And then you'd have to add all that together. That would give you a denominator without order. And then you would go back to your numerator and you would throw this in the garbage. Who the hell wants to do that?
Me.
Go ahead. Yeah, that is something that you would do. You're right. That is the kind of stuff that you do. Okay, so that's good enough for me.
Sure, I have a question.
Oh God, I didn't know what this question is turning into. Yeah.
Wouldn't it be easier to go indirect just by multiplying probabilities?
I did this so much. Yeah, you can go with but this took 2 seconds.
But you could just go. You could just go 7 over 7 times 6.
Yeah, so let's. I was waiting for somebody to say that.
Say
So
what?
5 over 7 times 4.
I was waiting for it. Okay, let's see if you get the same answer. What's the number here, guys?
180 over 343.
180 over.
343.
Okay, and what is that roughly to the nearest 100?
Something. 0.52.
So it's 52%.
Approximately.
Okay. Or, go ahead, Alexei.
7 over 7 times 6 over 7. So basically you're going indirect, solving for the cases where they're all different. So it's 6 over 7 times 5 over 7 times 4 over 7. And then it's just 1 minus that.
Oh, you want to just do.
And then you're solving.
You want to go 1. No, can't do that.
Why not?
Because you'll also get cases where you have 3 that are the same. Yeah, well, they want exactly 2 the same. So if you take away cases where they're all different, you're going to have cases where you have 2 the same, 2 the same, 2 the same, 2 not the same, 3 the same, 4 the same. No. But couldn't you still use your idea to do it another way too?
You would have to add additional cases. I mean, you would have to subtract additional cases.
Yeah, but I still think, yeah.
Oh, you could finish the question.
Yeah.
No, go on.
Okay, go ahead.
Oh, okay, for the 7, choose 1. For the question we did before, how come we don't square it? Because there's gonna have to choose 2 of the.
What did I write here? Choosing a box type for.
Double.
Does that represent choosing 1 box? No, it means which of the 7 box type are you going to choose 2 of?
Oh, so that's what I want to
There
ask.
is kind of one of us.
Okay, sorry?
The card type.
Yeah.
And then
No,
you're,
not box type.
then the assumption.
I don't know what it is, cards, boxes, it doesn't matter.
The
but-
assumption should be the cards should be infinite.
Yeah, isn't that that's what I said.
You said boxes should be.
Be- but it's the same thing because you have cards in the box.
Every box is a card.
You have 4 boxes, and then you have.
No, you have.
You have 4
choose
boxes, 7
4
cards,
boxes.
different kinds.
But the cards are in the box.
They're in the box. Look, let's say there's a.
Yeah, the box is 4
There's
boxes.
a smiley face card, there's a frowning face card, there's a weird face card, there's a mustache card,
She goes.
and there is a triangle card. And let's assume that they printed 50 trillion of these, and 50 trillion of those, and 50 trillion of those, and 50 trillion of those.
So 52.
And they also made 50 trillion boxes, 50 trillion boxes, 50 trillion. What's 4 times 50? 200 trillion boxes. And they took this smiley face and they put it in 50 trillion of those. And this, 50 trillion of these going to 50 trillion. So now you have 50 trillion boxes. Each one with this, 50 trillion boxes, each one with that, 50 trillion boxes, each one with that, 50 trillion with that. Now if you grab one of the boxes like that, you have gone down to blah, 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 trillion, whatever. 200 trillion less 1 box.
But your total kind that is printed out of the box is 7. Right?
Yeah.
Yeah.
Sorry, did I do 4? Yeah, sorry, here. Circle 1, 2, 3, 4, 5,
6, 7.
6.
You have to give it 7 instead of just
7.
4.
That's what I'm saying. So sorry, so 50 trillion times 7, okay?
That's what I'm saying.
So it's the same thing. You assume an infinite number of boxes, right? Such that when you grab a box, it doesn't affect things. Otherwise, what information would they have had to have given us as well?
So number of boxes.
There were, whatever, 500 boxes printed. Or no, sorry, 700 would be better. So it works evenly. So that way After you choose box A, right, box type A, now there are only 99 box A's out of 699 remaining boxes. But they didn't give us that, so we're just gonna, so how's the probability gonna be flat, like they say? Because you're so many boxes, it doesn't make any sense. Okay? My hand hurts. Next. 4.
4. Okay. Are we going to survive?
2 pair of identical cards.
7 choose 2.
Oh, 2 identical, 2 identical?
Yeah.
Hey, you know what's cool?
Yes.
Just for the hell of it, couldn't we do, Alexei, couldn't we use binomial now and take this away? Just to be fun, like to make it fun. You could do binomial now for 2 and then take that away. Watch. Okay, we'll use one method. We'll use one method. Method 1. She knows what I'm talking about. Oh, wait a minute. Method 1. 4 choose how many for doubles? 2 types, right? And once you're done with that, are you taking anything else? No. Because how many cards are you taking? 4. So this means double A, double C, or double D,
So isn't
double...
that 7 choose 2?
Yes. Okay. Done. Now we got to scramble. 4 factorial over 2 factorial over 2 factorial over 7 to the 4. Or, why don't we try this? If we use the binomial thing, we're going to go 7 times, what are we talking about, 2? So we're going to say 4 choose 2, 1 over 7 to the 2, 6 over 7 to the 2, minus part 3. I'm curious to see if we get the same answer. If we don't get the same answer, you need a new teacher because he doesn't know what I'm talking about. What does this work out to be? Do you understand this one? Now, in this one, notice I had a 7 choose 1, but then I had a 6 choose 2. Why don't I have any 6 business following a 7 choose 2? What does it say? Choosing a box type for what? You can't read my writing. Doubles. Now, here you're taking 2 box type for doubles, but how many total boxes do you need?
4.
So if you're taking doubles twice, how many total boxes have you taken by making this happen? If you choose a pair, how many cards do you have?
2.
And if you choose 2 pairs, how many cards do you have? 5. So this is like saying you have 7 different types of cards, you're choosing a pair twice. So how many total cards do you have by doing this? 4. How many cards do you need? Boxes do you need? 4. So you don't need to take anything else. Here you're taking 1 pair, but you need 2 more singles. So there's 6 different left. After you use that up, take 2 singles. You don't need any more singles. What is this?
18 over 343.
Just give me a percentage to the just give me a percentage to the nearest one.
5.2%.
5 point what?
5.2.
Okay, now give me this. Can you count?
That's 36 over 343. So
No, but what you have to subtract part 3.
I did.
You getting a different answer?
Yeah.
Oh my
Sure,
God.
you should retire.
I think I have to retire.
Maybe if I did calculation error, but
I hope so.
try again.
You retire on the 37th birthday.
So why is the binomial work?
It's not working.
Divide that.
It's not supposed to work.
It should work. Because we're doing binomial take away part 3. We're doing binomial minus this. What do you get when you do the binomial? Just the binomial, what do you get?
You get 36. So you get
What percentage do you get for this box?
10%, 10.4%. So you just get double that.
You get 10.4%?
Yeah.
But the solution to part 3 is like 52%.
Yeah.
So you're going to get a negative number. You get negative 42%.
Oh, because I include, just that? Just the upper portion?
Yeah.
Oh, my bad. Oh. I counted the bottom too. You get 70.8.
This gives you 70.8%.
I think so, yeah.
Sir, I think I know
What's the problem? Please.
I think there is 3 same and 1 different.
Oh! Very nice.
Wait, sorry, that's 62.9, sir. I
This is
cleared
nice. This is
62.9.
62.9?
Yes, sir.
She's smart. So it doesn't work. So what I thought, this is going to give you, remember this is, no. This is probability that you have 2 the same, right?
2 the same and
Success.
2 different.
No, this box just means 2 the same, right?
And,
And now, but it has, so that could involve 2 the same, or 2 the same, 2 different.
yeah,
So we
yeah.
took away 2, what the hell is this? This is 2 the same, 2 the same. So that should,
That's 2 the same, 2 different.
2 the same, 2 different.
no, this is both.
No, this is
No.
the same to the
2 the same, 2 different.
Oh, is it?
Yeah.
So this is 2 identical,
and
2
2 different.
different?
Yeah.
So I figured if we took away 2 identical, 2 different from getting exactly 2 the same, that we should get 2 identical, 2 identical.
There's a problem.
Show me.
Okay, the thing is, when you have 2 the same for binomial, when you have 2 the same and the other 2 can be same or different, when they're the same, the order,
Oh, I know. Yeah, keep talking. Keep talking.
order gets messed up.
What about?
It's, when you say 2 the same and you get the other 2 the same, the order is being injected like there, then for 2 different it's not, and then it gets messed up.
I don't follow.
Don't follow this one.
Because look, when you have two the same and then 2 the same, it's supposed to be multiplied by 4 factorial, 2 factorial, 2 factorial. But when it's 2 the same and 2 different, it's 4 factorial over 2 factorial. But those 2 are inside that, and we only have 4 factorial over 2 factorial multiplied by 2 factorial.
I'm not. I have to think about it.
It's the order. The problem is the order.
No, I'm sure you're right, but I don't. I have to think about it. I don't follow what you're saying. Check the book. Which answer are they going with? 52? The probability.
For 3, the answer is right.
No, for answer 3 they go with 52. What do they go with 4? They probably go with 5.2.
Yes.
They're going with this answer, right? So Milad is saying our little funky way of doing it here is we're doing that's a good question. I'll think about it. Because that way, 62 minus 50, that's 8. Our answer is like double.
Yeah.
It's too big. So this doesn't work. So I gotta think about it. And Milad, I think, has figured it out, but you'd have to articulate it slower for us. So we'll go with this. I'll think about it. I'm sure you're right. Okay, is there a question 5?
Yes.
What's part 5?
4 different cards.
All different? Okay, so you have 7. You take one of them, right? You can have all A's or all B's or all box 1s and then, and you don't jumble the order. There's one order. If you want, you can do that, but who cares? And then you're just going to divide that by 7.
Why did you choose 1?
Yeah, why did you choose 1 from 7?
Oh, sorry, what did we say? All different?
4.
Yeah.
Oh, all different. All different.
Seven,
All
four.
different, sorry. Yeah. Yeah. Now this represents a single, right?
4 different
Hang on,
cards
hang
from
on,
7.
hang on, hang on. This is no good. No good. No good. This is good. If they're all different, you want to count the order. Why are we counting order? Because we're forced to count order here, right? We talked about that.
Uh-oh, yeah.
Yeah, of course.
If you want, you could do this. If you want, you can do this. If you really want to, right? It's the same. It's the same thing, right? That's just 7b4.
There's B and C.
Okay. What's next?
Sketch a probability distribution for the number of different cards you might find in the 4 boxes.
So basically, sketch the probability. So sketch all of these.
How do we sketch?
Did we? It's easy. For the number of different. Actually, for the number of what?
For the number of different cards you might find in the 4 boxes of cereal.
For the number of different cards.
So I guess they're meaning like
But the problem is,
4 identical, 3 identical, 1 different.
Yeah, but you have to define this is a two variable plot. You're going to have a p of x as your vertical axis, and your x is going to be what? I think we have to do 7 different plots, don't we? Right? Because what is x going to be? Number of what? It's got to be either number of box type 1s you got out of 4 or a box number. So you would have 7 sketches. Agreed? Unless I'm wrong. Who agrees with me? You'd have 7 different sketches. You have to define x as something. Yeah.
I have a question.
So I'm not going to plot them. You know what to do.
I have a question.
Let me finish.
It says that it doesn't say anything about that each box has to have one card in it.
I'm assuming so. Where's the question? Here it says it does. Remember that each box has an equal probability of containing any one of the 7 collector cards.
It has the probability of having one and equal to each one. It can have
So what-
2, 0.
Containing any
Oh,
one.
okay, yeah, you're right. Technically, you're right. But come on, a kid's gonna open up a box of cereal. His friend gets 12 cards, and the other kid gets nothing. Or an IOU for 12 cards.
Yeah, I have iron.
Can you
Nice.
sketch it? Because we haven't sketched it all.
Oh, yes, we have. That was the first day.
I
I don't remember this.
don't know. No one remembers.
So you'd have to. No, I'm not doing so. So you'd have your first sketch. It would be
Just do one, yeah.
no. 0, 1, 2, 3, 4. This would be x1. What is x1 going to be defined as? Probability of getting box with card type 1 in it. You can have 0 of 4, 1 of 4, 2 of 4, 3 of 4. And then all you do is you go over each of the probabilities and you put them down. But you can't just use, like this 7, you've got to divide by 7 for your sketch, right? Because this corresponds to the probability of 4 identical. Okay, which could mean all box 1s, all box 2s, 3s, 4s, 5s, 6, or 7. So for this sketch, you can put, when you do the 4 identical case, which is, what does this work out to mean, 52%? This, for box type 1, has got to be 52% over 4, right? No, 7, right?
Sure, I'm confused. I don't even know what you're saying.
Happy birthday, sir.
What are you going to sketch? Define me your dependent and your independent variable. Your dependent variable is probability of x. And what is x?
Number of successful outcomes.
Per box.
Number of cards per box? There's 1 card per box.
Depending on for each cycle. So 4 identical cards for one
No.
case.
Define x for me. Define it.
Number of successful outcomes.
What is a successful outcome?
I'm confused.
Yeah, me too, because you haven't defined it. The random variable x is going to be what?
Why didn't you define it?
I did.
What is it?
There are 7 different ones. One is probability. I decided x1 is going to be the probability of getting box 1.
For all 4, for 1, 4 for what?
From 0 to 4 successes.
Okay,
So what's the domain of the random variable x1?
0, 4.
You could have 0 ones, 1 1, 2 ones, 3 ones, or 4 ones.
Okay.
And there's a probability associated with each of those. You plot it. And guess what? That's going to be the exact same graph for
Each one of them.
this. And it's going to be the exact same graph for this, for this, for this, for this, and for this.
So can you sketch it?
So there's the equal distribution?
No!
Alright, yeah.
It means that you're going to have movement in the distributions, but each of the 7 distributions looks the same.
Oh,
Because
okay.
the proportion of a box of card types in each box is equal. So, you tell me. You do it. You tell me. 0, 1, 2, 3, 4. What was the probability? Okay? So 0 means that you get, that they're all different. No. Sorry, that you don't get a particular type. So you can do it this way. I don't know if we have it somewhere on the board. You can say 6 out of 7.
Shouldn't we just put it in the binomial?
Here, isn't it just 6 over 7 to the 4th?
Yeah.
Isn't just 6 over 7 to the 4?
Yeah.
Meaning that you don't get any of box 1.
Yeah.
You don't get box 1, you don't get box 1. So what is that as a percentage? What's 6 over 7 to the 4?
53.9.
53 point what?
9%.
Okay, so
54.
this is 1. That's 50. Here.
I think so.
Okay? Next. What's the probability of getting only 1? Did we do that already, or do we have to? Yeah, I think we did
No,
it.
we did 4.
That's right here. No. No. Now here's the thing. Yeah, what's the
that's
probability of
right.
getting only 1? Exactly 1.
It's not that, sir.
It's more identical.
Okay, fine. If you're gonna get exactly 1,
It's 4 choose.
but we have to do,
So just put it in the binomial formula. 4 choose.
Gosh.
so many, I know. Just, okay, fine, we'll use your bunny on that. The one that I showed you how to do. But if you do it, you're not gonna use a 7 multiplier here, right? Because I'm graphing it for 1.
Yeah.
So you would just have, if you want to do it that way, you would have 1 over 7 to the 1, 6 over 7 to the 3, 4 choose 1. What's that? I mean, you know what to do. You don't need me to do it.
Okay, then what do we do? Connect the dots? What do we do?
You never connect the dots.
Just branch it.
Ever in life. Don't
So
ever
there are
connect
4,
dots.
There are 5 dots.
I've taught you that already too. Curves the best fit, lines the best fit.
So there are 5 dots.
35.36%. Approximately.
Sure, but on the book, it should be the vertical line like that.
Can I please finish?
Sure.
Next, 2 the same. Right?
But sir, you said that the other cards might be the same too. Might be identical too. So.
Yeah, but
It doesn't
that's,
matter.
it doesn't matter. I'm doing this.
8.9.
This is a different question they're asking now.
No, about approximately 9%, sir.
9 times 4 is 36. So 1, 2, 3, 4.
About 9. This one? 35, 36.
4 choose 2.
You guys really need me to do this?
No. I'm fed up with this.
So how would you draw like it gets so like about what?
You just do a sketch. It's not a graph. You're providing a sketch, and you do not connect the dots ever.
No, I think you should do like this.
It is not a universal probability distribution.
So there's a C part.
He is telling me the sketch should look like this.
Oh, it's no. You can do like this. It's
Oh, you want lines from underneath? No.
yeah.
No.
That's what it did do on the book.
So they do it in the book. Who would you trust more, the book or me?
The book represents
Really?
represents
All those hard questions where the book was wrong and you had to use me to answer the questions, you still trust the book?
it represents a
So
group
the
of
book
people.
was made like what? 20
It represents a group of people, and yet we found tons of mistakes in the book.
Of course.
So
It's just
if you
Don't trust the book, don't trust me. Trust your brain. How many of you guys put
can.
lines underneath dots for graphs? Whoever builds graphs like this? Who does that?
Bug.
We don't do that. We do this, and we do this.
Another question.
Or we do this, and we do this.
On our test and quiz next week, we will any simulation question.
No, how can I make you do a simulation on a quiz or on a test?
No, because there are many questions of simulations. In
Use your brain. Think about what you just asked me.
Simulation, you have to experiment.
How
So
can
you
we
ask
design a
No,
simulation?
like design a simulation, not do a simulation.
So how can we do this?
Do we have to design a simulation?
No, man.
How would you design a simulation or the test on pen and paper?
No, there are lots of questions in the book.
Take a paper bag. Take
the techniques of
3
this
green
section.
jelly beans, 6 white jelly beans,
Yeah,
4 blue
that's
jelly
what I was
beans.
saying.
Put them all in the bag, mix them all together. Take one out, record the result,
Yeah.
put it back in, mix them all together. You think I want to read through that?
Maybe.
Mr. Gallon will do that.
Yeah, Mr. Gallo would
There's
do
no
that.
way he's going to do that.
Because
Gallo's a very smart man. He doesn't want to read through that garbage either.
he usually gives us some basic concept questions to
Has he ever asked you to design a simulation on
No,
a test?
but asking definition questions is basically.
Yeah, definition
No.
question. Fill in the blank.
Definition is not design a simulation.
This is stupid as that.
No, it is not. A definitional question does not mean design a simulation. Design a simulation means computer programming. You know what simulation design would be good? You know that really hard question from before that I told you the book was wrong on? That would be good. If you guys are from computer savvy, you design a simulation with a random number generator, get it to give me an answer. Then we know who's right or who's wrong.
Do you get marked for it?
Shit. Can we get out?
No, too late now.
So
No, it's not
part
late.
C.
Just
Tomorrow.
we have 15 minutes. It's Saturday, so
Tomorrow.
Monday.
Tomorrow, we're coming to prepare tomorrow.
Let's do any other questions you have.
So there's part C, there's part C.
What the hell is part C?
I don't even want to take a look at it.
It's
Is the distribution in part B uniform?
No.
Is part B uniform?
No.
So what is uniform?
Uniform is the thing you wear on your body, and everyone wears the same.
Let X be defined as the possible outcome you could get from rolling a die. What are the possible outcomes? 1,
Over
2,
6.
3, 4, 5, or 6.
1 over
If
6.
you roll a die, what's the probability of getting a 1? If
1 over 6.
you roll a 2,
1 over 6.
so PXI.
And sir, you should write a vertical line.
Don't write a vertical line.
Okay, so what is uniform?
It's uniform. The probability of X, right,
But it doesn't change.
does not change.
But
Dependent. It does not. It does
so
not
the
matter.
answer is not, it's not uniform.
Right.
Okay.
Okay, it's not uniform.
Well, it's good to know that we got a question.
Can we have our test back?
Yeah, sir, please. I think we have enough time.
Right, I said that I was not here for that.
Maybe what?
Yeah, ready for this?
You want experience?
I don't know.
Where do you want to go?
Like, can I change?
Yeah.
Sir, can we have our test back?
Yeah, we can help you with it.
You get it tomorrow.
Tomorrow is Saturday, sir.
You get it on Monday.
Why not today?
Because it's too late.
No, you have to
I
get
don't want to explain why. It's too long. I have to enter. I have to this. It's going to be on Monday. You have other questions though?
So let's talk about your birthday.
What's your birthday today, sir?
What?
Actually.
I have a question.
You guys have other questions?
Yeah, it's only one.
Huh?
Okay, so it's on page 405, number 16. Blue? Okay, you start at the corner 5 blocks south and 5 blocks west of your friend. You walk north and east while your friend walks south and west at the same speed.
Is there a picture?
No.
Wait, what question?
Okay, read it again. You start.
At the corner 5 blocks south and 5 blocks west of your friend.
Okay, hang on.
You walk north.
Wait.
You walk north and east.
Oh, wait. Start 5 blocks south, 5 blocks west, and 5 blocks south.
Yeah.
Okay, so this is the friend, this is me. So wait,
Oh, wait, no.
1, 2, 3. Yeah, go ahead.
You walk north and east while your friend walks south and west at the same speed.
Okay, so you're going this way. I remember this question. You're going this way and they're going that way, yeah?
What is the probability that the two of you will meet on your travels?
Okay, if they're gonna meet, if you assume they're going at the same speed.
No.
You're going to assume that the speed of both friends is the same. You're going to assume that they both start at the same time, and you're going to assume that their speeds are constant. So if they're going to meet, and they said that this guy's only going blah blah that way, this guy can't go back south and west, and this guy's going this way, working down this way, or this way. This guy can't go back up. Yes.
It doesn't matter if the speeds are constant.
Huh?
It doesn't matter if the speeds are constant.
Okay, that's true. As long as the speeds are the same. But it does mean that if this guy's speed varies, this guy's speed varies exactly the same way. So you have to have this effect. Right? Or it's easier to just think of it. So if they're going to meet, they've got to meet along this line, right? They've got to meet halfway. If they are going to meet, they're going to meet there. So the total number of possibilities that this region is going to be anywhere. This guy can be anywhere, and this guy can be anywhere. And successes are going to correspond to them both being at the same dot. How many dots are there? So there are going to be 6 possible areas of success. You're going to add them all together because those are exclusive possibilities. Whatever. Let's just do the question. Let's just do the question. Probability of success is equal to the number of ways you can succeed divided by NS. Agreed? Sure. Let's calculate NS first. Why not? Let's take a look at NS.
All the possible points.
NS is going to be all of the places me can exist here and F can exist here. How many ways can me get to here? Me can go, me's got one way to do this, doesn't it? I can only go this way, because I can't do this. Look, I can't go like this, like this, like this, like that. I can't go back, right? I'm always going east, so I can go here, 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 here. Seems to me there's only one way I can get here, right? How many ways can I get here? This way.
It's 2 ways.
No, many ways. Many ways.
That's one pathway.
4,
2, 3,
5.
4. Don't we have to do the thing we used to do? Remember the Pascal's method? Look, to get to here. How many ways can I get to here? 1. To here, 1. To here, 1. To here, 1. How many ways can I get to here? 1. How many ways to here? 2.
3.
1 and 2 is 3. 4, 5. Okay? So this is a 1 here. This is a 5. What about here?
7. That dot is 7.
What is this? Is this a 2? So is this a 3?
3.
5.
5.
What is this?
2, 3.
Is this a 3 here?
No, 2, 3.
That's a 2.
No, look. Well, 1 and a 2 is a 3.
Yeah, 3.
And a 3 and a 3 is a 6. And what is this, a 4?
Yeah.
So this is a 10. Right? I'm assuming that this is also going to be a 10. No, I don't.
It's especially this special one.
What is surprise?
Okay, so how many ways can I get here? I have 20, 32. But how many ways, and hang on. No, wait.
I don't know.
Yeah. So, total number of ways of success.
That's what it says in here.
We can both meet here, or we can both meet here, or we can both meet here, here. Now, how many ways can we both meet here? I have one way of getting here, and that person has one way of getting here. But wait a minute. How many ways can we both meet here?
5 different ways.
5 squared.
Oh yeah, because you can take 5.
Because for every one of the 5 ways I can get here,
He can take another 5 too.
he can take,
5 different other ways.
right? So I think, oh sorry, I'm doing this first. It looks like I'm doing this.
That means successful ways, right, sir?
Yeah, this is successful ways, I believe. We'll think it through, unless you think I'm wrong. I think this makes sense.
Squared plus 5 squared plus 5 squared.
How many total ways are there across the board? 20, 32. There are 32 ways I can get to this midpoint, and there are 32 ways that he can get to that midpoint. 32 ways times 32 ways are the total number of ways we both end up here. We could both end up in the same spot here. I could be here, he could be here, I could be here, he could be here, we could both be there. What does this work out to be? What's that?
25 plus 1 plus 25 plus 100 plus 100 plus 20.
It's 152 over something.
Just give me the percentage.
24.6%.
24.6%?
6.
What did you say it would be, Jeremy? 1 out of 36?
Maybe, I don't know.
What's 1 out of 36?
That's so small.
Thought it through.
Let's see what the group of the book say.
That's like 2.7% for the answer.
I'm not so confident with my answer, so
What pages? 4 or 5?
I'm not so confident with it.
Let's see what the moment of truth.
Hopefully they get a similar answer.
Question 16.
4
I
or
don't know.
5.
I have to think about it.
Question 16. 63 out of 256. So
6 times 4 is...
24.6. Your answer.
Why do you know I'm right? How do you know I'm right? You're assuming the book is right.
Find the book and your answer matches.
Based on
a group of people.
The book and I agree. Now, I don't know if I agree with it. But I'll tell you right now, I don't feel very confident in that answer, but I think it makes sense, but I'm not positive. I wouldn't bet money.
There's somebody thought of